Hello, you're with us again on Chemistry in Action. In the last few episodes, we studied different types of organic molecules. You should remember them: the hydrocarbons and hydrocarbon derivatives containing oxygen, nitrogen, the halogens. We will see some of them again today. The molecules we will study in this lesson are made up of these small organic compounds, this time linked together to form long-chain associations called polymers. By the end of today's lesson, you will realize how much we depend on polymers for many of our daily activities. We'll be back to start our lesson again after these messages. Polymers have been around us for a long time. Look around you. You use materials composed of polymers every day without realizing it. Rubber from the rubber tree, silk from silkworm cocoons, or piña fabric from the pineapple plant are examples of polymers which we have learned to extract from natural sources and process for use. There are also the man-made or synthetic polymers. Examples of these include nylon rope, polyurethane foam, PVC pipes, and perhaps the most familiar of all, polyethylene products, to which we give the catch-all name plastics. We have thus seen one way of classifying polymers. They can be either natural or synthetic. The majority of the polymers we will consider today are the synthetic type. In the next episode, we will discuss the natural biological polymers. What are polymers? Polymers are very large molecules made up of thousands of small, simple, repeating units called monomers. If this string of beads was a polymer, then each bead making up the necklace would be a monomer. A polymer composed of a single type of monomer is called a homopolymer. All the beads in this so-called polymer are the same. It is a homopolymer. It is a copolymer if there are two or more types of monomers. This necklace would be a copolymer of beads of different colors. The monomeric building blocks of the polymers we will study today come from the different classes of organic compounds we learned about earlier. The simplest of these are polymers from alkene molecules. Let us start with the simplest polyalkene, polyethylene. It is a polymer from the alkene ethene or ethylene, which is two carbons. The double bond of ethene contains two pairs of electrons. Under conditions of high pressure and temperature, ethene molecules can be joined together to form a new compound, polyethylene. In the course of the polymerization reaction, the unsaturation or double bond is lost. One pair of electrons is used to form covalent bonds with two other molecules of ethene. Thus, the product is fully saturated. Hundreds to thousands of monomer units can add together to form polyethylene. How do we write the molecular formula of such a gigantic molecule? We use a shortcut method. To write the molecular formula, place the monomer unit within brackets. Add bonds on either end of the monomer to indicate that the chain extends in both directions. The subscript N tells us that there is a large and specified number of monomer units in the full polymer structure. This formula denotes the polymer polyethylene. Although polyethylene is made from ethene monomers, the properties of the polymers are not necessarily the same as the monomer. If you recall the properties of ethene, it is a molar mass or molecular weight of 28. It is a gas at room temperature and is quite reactive. What are the properties of the polymer? Polyethylene, with a molecular weight in the range of hundreds of thousands, is solid at room temperature and a rather stable, unreactive compound. Polyethylene is familiar to us as the soft, lightweight plastic bags we use every day, or as tough, rigid plastic molding of things at home or in school. So then you might ask, how can objects made up of the same material exhibit such different properties? The answer lies in the process used to make the polyethylene. Two slightly different forms of polyethylene can result depending on the manufacturing conditions used. At a pressure of 5 to 30 atmospheres, linear polyethylene molecules called high-density polyethylenes are produced. The linear chains can pack closely, forming an ordered quasi-crystalline structure with high rigidity and high tensile strength. High-density polyethylene melts at about 135 degrees Celsius. High-density polyethylene products are usually colored, opaque, and are formed in molds. Threaded bottle caps, TV cabinets, beer crates, or toys are some examples. In passing, we note that the term plastic comes from the Greek word plastikos, which means capable of being molded. The other type of polyethylene, low-density polyethylene, is formed at 100 to 300 degrees Celsius and 1,000 to 2,000 atmospheres pressure. The chains are branched or cross-linked and therefore cannot pack together tightly, hence the term low density. Low-density polyethylene is waxy, semi-rigid, transparent or translucent, and melts at a temperature of 110 degrees Celsius. Refrigerator dishes, electrical insulation, and soft drink bottles are some of the materials made out of low-density polyethylene. So, using polyethylene as an example, we have seen the enormous difference between the properties of the monomer, ethylene, and the polymer, polyethylene. Let us look at another alkene that is also a gas at room temperature, propene or propylene with 3 carbons and 1 double bond. The structure of polypropylene is very similar to polyethylene, except for a methyl group that sticks out of the main carbon chain. Polypropylene is used in rice sacks, candy and food wrappers, cigarette wrapping, adhesives such as tape. So you see that different organic molecules can be used to give polymers with different characteristics and different uses. For another example, let us consider chloroethene. Its common name is vinyl chloride. The polymer is polyvinyl chloride, or PVC.